Okay, so let's begin. We're going to start off this lesson where we're focusing on maximum and minimum points. Further, from our lesson in last class, I used the term local max and local minimum quite a bit, but today I'm going to define it more so you have complete understanding. Remember, this module 3 test is going to have more multiple choice. Then it's very hard to have multiple choice on just basic derivatives, but it is easier going forward for module 3 and module 4. We're able to introduce concepts that have multiple choice in them. Now remember, don't bank on the final exam being all multiple choice. It's very hard to do that in a calculus course. And for those of you who have chosen that as an option, short answer questions will probably be part of the final exam. Okay, so we will be defining this local extrema or local maximum and minimum points in the lesson today. First question is very similar to last class, but as the question reads, we are asked to find all our local extrema. That is still, let's go out of full screen mode. Make sure I'm on highlighter mode. Still not working. There we go. So not only are we going to determine the local extrema, but we are going to be using critical numbers and our first derivative test in order to do so. Once we get to optimization, I'm going to give you clear step-by-step process about how this process is very similar to the steps in optimization. However, it's a good idea in your study notes that you include step 1, do this. Step 2, do this. Step 3, do this. Language is very important to help you remember the steps of mathematics. So we have our original equation. Remember, there's no product, there's no quotient, there's nothing too complicated. So I know I'm going to use the power derivative rule to simplify this. I believe very similar to our example in last class. 6, and -36 all have the greatest common factor of 6 in common. So we're going to take the 6 out. Now, remember, we learned in the last class that the local extrema occurs when the sign of the derivative changes. So if the sign of the derivative does not change, you don't have any local extrema, no local minimum or maximum points. If I set or first factor x squared plus x minus 6, I'm going to get x plus 3 times x minus 2. Now, remember, where the derivative is equal to 0, the roots of the derivative are equivalent to the local maximum and minimum or potential local maximum and minimum points in the original graph. So that means if I'm solving for the local maximum and minimum points in my original graph, I do need to set the derivative equal to 0. That's very important. And to understand why we're doing that, I had a table in my last class that really described and showed how the local maximum and minimum points connected to the first derivative. So when I set those binomials equal to 0, I can solve for x is equal to -3, x is equal to +2. Now, these are critical numbers. Not only do they represent the x-intercepts of the derivative, but I can use these critical numbers to plug in to the original function in order to get critical points. Okay, so the x-intercepts of my derivative can be used to plug into my original function to get critical points. Now, why wouldn't I just substitute the x-intercepts back into the derivative function? Think about that for a little bit. Does anybody know? what would I get if I plugged in x is equal to -3 and x is equal to +2 into my derivative equation? Remember the x-intercepts of the derivative. So at the x-intercepts, the derivative is equal to 0, right? So if you plugged the x-intercepts back into the derivative function, you would just get 0. You would go nowhere. It would hit a dead end. So that's why it's important to remember that we're plugging it into the original function. So these critical numbers now become critical points only when I plug it into the original function. So I would find f of -3, not f prime of -3, f of -3 and f of 2. Very important step. This is probably the step that will take you the most time, taking your time and plugging it into the equation, because if you don't have the correct critical points, then you're not going to have the correct maximum and minimum points, right? The -3, +86, +2, -39. The y values are important because they represent a potential minimum or maximum point, but we don't need to use the y values when we do our first derivative test table. So when I set up my table, I have my x values of the critical points, right? And graphs in calculus, they always extend towards -infinity and +infinity. So unless you're talking about a real life application, like we did at the end of our last class when we were talking about a symptomatic person and how the first derivative helped us figure out when their temperature was increasing and decreasing, those intervals. In that particular case, because we could not have negative days, our D value or days or our range started at 0. But whenever you don't have a real life application and it's just a generic algebraic polynomial equation, we're going to start at -infinity, end at +infinity, and you always pick a test value in between those ranges. So in between -infinity and -3, I'm choosing a value close to my critical point. So I'm choosing -4. You can choose -5. It really doesn't matter, but I like to choose values very close to my critical point. In between -3 and +2, I could have chosen +1. 0 is very easy to plug in. So when you're able to pick 0, try and pick 0. And in between 2 and infinity, I pick the closest number, +3. You want to avoid fractions and decimals when you're picking your test numbers because there's lots of room for error in those calculations. Okay, my next step is to take my first derivative. And now I'm going to plug these points into my first derivative equation. Okay, plugging in the test values. I know I'm not going to get 0 because the only way to get 0 is from the points -3 and +2. Those are the roots of the first derivative. So when I plug in -4, I get a positive. When I plug in 0, I get a negative. When I plug in 3, I get a positive. What does that mean? Well, that doesn't mean anything about the first derivative, but what it does, well, it does mean something. It means that the graph is above the x-axis in between -infinity and -3, below the x-axis in between -3 and +2, and in between +2 and +infinity above the x-axis. So it does mean something, but we're more interested in the original function. When the derivative function is above the x-axis, we know the very first rule we learned in curve sketching is that represents an increasing interval. Then a negative in the first derivative below the x-axis corresponds to a decreasing interval. So we have two increasing intervals and a decreasing interval here. When I move from an increasing interval to a decreasing interval, am I going to hit a maximum or a minimum point? Yes, Jola? A maximum. So I know that my critical point, -386, represents a local maximum point. Also, this chart tells me, so remember this, I said last time, this is what a graphing calculator does. The algorithm on Desmos or any type of graphing calculator is based on this. This is how the graphing calculator knows which intervals are increasing intervals and which are decreasing intervals. I was just talking to my friend's son at University of Waterloo, who's in computer science. And he said he can't believe his whole computer science course is like 10% programming, 90% math, because so much of developing algorithms is a clear understanding of the mathematics behind it. And something as simple as a graphing calculator algorithm requires this calculus, right? You would, and there's kids who are doing projects on video games. There's so much math, including a branch of calculus that I haven't taught you and unfortunately won't be able to teach you in this course, lines and planes that are in the art of video game design and the programming of video games, switching from lines to planes to every perspective. That is mathematics right there. Okay, so moral of the story, you computer programmers will appreciate me next year when you're doing all your math. As we move from a decreasing interval to an increasing interval, that is always a minimum. And we're going to define local maximum and minima again. So the last part of the question would just be to define the intervals of the increasing intervals and the decreasing intervals. I put it in this notation is because this is what your textbook often does. All this means that the range between -infinity and -3 and the range between 2 and infinity are increasing intervals. In regular Mary Ward, we would focus on this notation a little bit more, but there's just not enough time. So even if you just put a comma or an and, that's fine for these quadmesters, right? We can't be such a stickler on notation because this is not a regular way of teaching calculus. Okay, so something that might appear in multiple choice, yet last class we examined quite a bit of graphs and dissected and interpreted the graphs in a very detailed, thorough way. We also can bring up some definitions. So let's look at these local extrema, also referred to as turning points. So in your unit guide, when you're doing your curve sketching, reading through curve sketching, you'll know that notice that local extrema and turning points go hand in hand. So when we talk about local maximum, that is defined if the y-coordinate of all points in the vicinity are less than the y-coordinate of that particular point. The sign of the derivative would change from positive before the point to 0 at the point and negative after the point. It's a real definition. We go from positive to 0 at the point to negative, right? That's a local extrema. And it says points in the vicinity because you can have multiple local maximum points. The pinnacle local maximum point would be like the real maximum point. But because a polynomial equation moves to -infinity and positive infinity, you have to keep into consideration or take into consideration that you cannot see the entire graph in the particular range that you have in front of you. So there could still be a full maximum point. That's why we always call these points local max or local min. When you did grade 10, for example, and you had a clear ending to your quadratic function and a clear beginning to your quadratic function, we would just call it maximum and min. But always take into consideration that your graph is going all the way from negative to positive infinity, and you can't see all possible maximum and minimum points. The only contradiction to that rule is also that example of real life examples that I went through last class, where you have a very defined domain and range. So the local min, right? These are all points in the vicinity. The y-coordinates of all points in the vicinity are greater than the y-coordinate of the point. So the sign of the derivative would change from negative before the point to 0 at the point and positive after. Now, what I was talking about, we sometimes say global, but an absolute maximum or minimum point is of f of a is the biggest or smallest value for all x in the domain. So that only applies to those real life situations when we can really define and see all x values in the domain. But if we cannot, we can't call it an absolute maximum or minimum. So the next graph is going to have a defined interval. So this is an example of a defined interval. If you can see that graph a little bit, I'm not sure why it's going off the smartboard, but we have a defined interval in between 0 and 10. So if I wanted to identify all the local maximum points, well, I'm not talking about absolute. Well, yeah, I could say that D is the absolute maximum point and A is the absolute minimum point, because that is the value that is greater than Y value that is greater and the Y value that is the least value. But when we talk about local maximum points, well, B and D would qualify as still maximum points. Even though D is the absolute maximum, it still falls under the category of local maximum. B and D would be local maximum points, whereas C would be a local minimum point and A being an absolute minimum point. Now, something that all these local max and local points have in common, they each would have horizontal tangent lines. That means the derivative at those local max and local minimum points, the derivative is equal to 0. The slope of the derivative function is equal to 0 at all those points. That is definitely something that could come up as a multiple choice question. Now something else that we want, I think we looked at last class, a critical number of a function is a value of A in the domain where the derivative is equal to 0 or the derivative does not exist. So yes, our last lesson was really very much focused on critical numbers and critical points. But let's go through some more specific scenarios before we end off our lesson with a few examples. So I'll give you a second to just examine these a little bit. We looked at the first 3 last class, and this is something that has to be in your study notes. It's very important for it to be included in your study notes for module 3. Okay, so let's look at when the derivative is equal to 0 and when the derivative does not exist, okay? So one potential scenario when the derivative is equal to 0 is we have a local minimum point. That would be the case at for this graph of f of x is equal to x squared minus 6x plus 8. We could also have the derivative equal to 0 for this cubic function, where there is no local maximum or minimum, but we have this funny situation here where we kind of have, we still have a horizontal tangent line at the point of the y-axis. So that still counts as a situation where the derivative is equal to 0. Now, at a cusp, we have a local minimum point. So that will still result in the behavior of our derivative function, the graph of the derivative function switching from below the x-axis to above the x-axis. We included that example in the study notes yesterday. However, the derivative does not exist. That means that the derivative function will have an asymptote when there's a cusp, but let me remind you that the limit still exists. We learned that in module 1, and there is still behavior before and after that point where the derivative does not exist. So we still have a graph that we can draw from a situation where there's a cusp. Now, this type of graph also, over here, we have a derivative that would not exist. So an example would be x to the power of 1/3. And that is, even though it there's a certain behavior that mimics it there, there's no minimum or maximum point. And in this particular situation, f of x is equal to 1 over x. The limit, the derivative does not exist, and there is f of a also does not exist. We have an asymptote. Therefore, a is not a critical number. So when you have an asymptote, you don't have a critical number at that particular value of a. So whenever we are looking at finding local minimum and maximum points, you want to find the critical numbers, right? Substitute the critical numbers, and also you want to find the x coordinates of the endpoints of the interval in the function. This more pertains to when you're getting a defined interval or when you have a word problem. Whenever you have a word problem real life application, you need to have defined endpoints of the interval into the function. That is very important. So we're going to draw on 2 examples that don't have graphs, right? We can always check our answers using graphs, but the whole point of curve sketching is that we don't necessarily have to see the graph. We can do everything algebraically. After the last test, I had a lot of kids say, you know, I really like the algebra. Well, calculus is a lot of algebra. That's why first year calculus, they tell you you're not allowed to use a graphing calculator or a calculator in general for any of the tests, because they're teaching you strategies on how to compute, how to make your brain the calculator, how to make your brain the algorithm, right? You're learning the algorithms that way. Okay, so this slide has an example. Oh, I think Mr. Bullock forgot to include this. Let's see. We have the cylinder. Oh no, it's just a little bit mixed up. Okay, no problem here. We'll start with this, example 2. Find the absolute max and minimum of the function on the interval between -3 and +4. So our first couple of steps are the same. We want to first take the derivative. Step 1 is always take the derivative. Here we're using the power function to take the derivative. Then we are going to factor. I'm going to take the greatest common factor out. That makes this more simple to factor. I can clearly see x squared minus 4 can factor to x minus 2 times x plus 2. Please be careful when you're doing difference of squares. That's a common place students made mistakes on the last test. You set that equal to 0 and solve for x. So that means that +2 and -2 are critical numbers. But in addition to +2 and -2, we also test the endpoints of the interval. So now we have more critical numbers than just the x-intercepts. We also have -3 and +4 as potential critical numbers. So when we are plugging in -3, I get a y value of +6. When I plug in -2, I get a y value of +13. When I plug in +2, I get a y value of -19. And when I plug in the endpoint +4, I get a y value of +13. Now, when I'm considering absolute minimum, I'm looking at the x and y that gives me the lowest y value. In this case, it's x is equal to 2, y is equal to 19. That is the lowest y value. So that's why it's the absolute minimum point. Only because this is a defined interval. Otherwise, it would be a local minimum point. For an absolute maximum point, oh, I have 2 potential absolute maximum points. When x is equal to -2, y is equal to 13. And when x is equal to +4, y is equal to 13. That's why we had to also test the endpoints of the interval. So our absolute maximum, so -3, +6 would still represent some type of local maximum or minimum, But when we're talking about the absolute maximum or minimum, we have two of those because we have the same y values. Those y values are larger than +6, and they are the largest values out of my critical numbers. So if you only test when you have a defined interval and you only test the x-intercepts, or the critical numbers derived from the x-intercepts, you would lose some marks there. And the final question, which relates to our next module on optimization, you're going to have a lot of questions like this in module 4 when we're looking at cylindrical containers, just different geometrical shapes and the volume and surface area for that. Main reason optimization is extremely important in engineering, and shapes in general, geometric objects, very important for engineering. So it says the surface area of a cylindrical container is to be 100 centimeters squared. The volume is given by the following function, where R is the radius of the cylinder in centimeters. Find the maximum volume, That's what optimization is. Find the best way of doing things, right? Minimum volume, maximum volume. You can relate any type of situation to optimization. When you have a business, what is my optimal selling price? What is my optimal revenue based on this criteria? Optimization just is one of the most useful concepts I think I've ever learned. So if the radius cannot exceed 3 centimeters, we have a restriction here. The radius cannot exceed 3 centimeters. So that is one. Let me get out of this mode for a second. And I want to switch to my pen. Okay, so the radius cannot exceed 3 centimeters. So I have a stipulation here that R has to be between, it cannot exceed 3. But I can also say that I have another restriction on the interval. What would that be when we're dealing with measurement? What is the smallest possible value of R? Yes. 0. Yes, very good. But whenever I'm dealing with measurement, I have to have a minimum of 0 because I can't tell you to go measure negative 70 meters out there. I can't ever talk about negative measurements. So we take our volume equation. The first step always is to find the derivative. But we have to remember that in addition to finding our critical numbers from our derivative equation, we have to test the endpoints of the intervals. So I'm going to find my critical numbers by setting my derivative equal to 0, and I'm solving for R. Notice with real life scenarios, my R, I didn't want to do that. Yes, okay, back to full screen. So my R is a radical, right? We have a square root there, we have pi. So one tip that I want to tell you that I learned from watching a lot of solutions on the last test, try to keep your answers in exponent form until the very end. When students try to work with radicals, like I think if it was Mr. Bullock and myself working with radicals from the beginning, we're experienced mathematicians. So, you know, it's easy for us to work with radicals. You should work with exponents as long as possible and convert to radicals at the end, right? Because otherwise it's hard to see what can be combined and what cannot be combined. Anyway, so here we have an R value. I would consider plus minus when I'm going from R squared to R, but I'm not going to consider minus in this situation a negative value because there are no negative measurements. So this is my positive radius that I'm dealing with. The radius cannot exceed +3. So when I'm plugging radius into my original volume equation, I'm going to test the volume of 0, which because there's R in both components of my original volume equation, I will have an endpoint of 0. I have testing my R critical number that I've come up with. That gives me 76.8 centimeters cubed. And when I plug in a radius of 3, I get a volume that is less than that. That means that I'm going to pick the volume that has the largest number, because I want to know the maximum. So the maximum volume of the cylinder is 76.8 centimeters cubed, and that happens at a radius of about 2.3, because if I convert this on my calculator, the square root of 50 over 3 pi, that's about 2.3 centimeters. Okay, so this is a clear application derivative question that is related to engineering, manufacturing, anything like that. Okay.